You are already at the center of the universe. Not metaphorically, physically, measurably. Every direction you look, the universe extends the exact same distance before the light runs out of time. Scientists confirmed this in 1965. Most people still have no idea what it actually means. The observable universe is 46.5 billion light-years across, not 13.8. Even though the universe is only 13.8 billion years old, because space expanded while light traveled. Beyond that boundary, at minimum 250 times more universe continues, and in 2023, the Planck satellite measured the curvature of space to within 0.4% and found it perfectly, impossibly flat. Tonight, we'll find out what flat geometry means for an infinite universe. We'll cross the cosmological horizon and discover what's waiting on the other side. We'll uncover why every point in existence is simultaneously the center, and we'll reach the one question cosmology cannot answer and why it may never be able to. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. The night sky is lying to you, not about the stars, about what you're actually seeing. What reaches your eyes when you look up isn't the universe. It's a fraction of it, a carefully bounded, physically constrained fraction defined not by the size of space, but by the age of time. And that distinction changes everything. The observable universe is a sphere, 46.5 billion light-years in every direction. A hard edge, not a wall, not a substance, but a horizon. Beyond that horizon, space continues. What doesn't continue is the light that had time to reach you. Here's the part most people get wrong. The edge of the observable universe is not where space stops. It's where your clock does. Light travels at a fixed speed, exactly 299,792,458 meters per second. The universe has had 13.8 billion years since the Big Bang. Light traveling in those 13.8 billion years can cover a specific distance, no more. But here's the strange part. The observable radius isn't 13.8 billion light-years. It's 46.5 billion, more than 3 times larger, because space expanded while the light was traveling. A photon released near the early universe began its journey when those distant regions were much closer. Space stretched beneath the photon as it moved. The region it left was carried far beyond where a simple calculation would place it. So the edge you're looking toward isn't a location in space. It's a moment in time. And here is what the Planck satellite confirmed in 2018. Beyond that edge, space does not stop. The universe continues with no measured sign of curvature, no boundary that any current physics can identify. 250 times larger than what we observe is the conservative estimate. Most models require the words effectively infinite to describe it. But here's the piece almost nobody talks about. The horizon isn't fixed. And it isn't shrinking in light years, but in what it can actually tell you. It's shrinking right now. There are already regions of space from which light will never reach you. Not because they're too far, because the space between you and them is growing faster than light can cross it. The photons left their source, pointed in our direction, and are losing ground. Those regions, whatever they contain, are permanently beyond your knowledge. Not temporarily. Not until better technology arrives. Permanently, by the laws of this universe. And the horizon has a second problem. Something that rewrites the question entirely. It isn't yours alone. Here is the fact that took cosmology decades to fully absorb. There is no center of the universe. Not because the universe is large, because it's structured so that every point simultaneously qualifies as the center. Every single observer, everywhere in the universe, is at the center of their own observable sphere. The horizon doesn't mark a distant location. It moves with you. Wherever you go, it surrounds you at the same distance. You are always at the center, because the center is wherever you are. This has a concrete physical cause. Arno Penzias and Robert Wilson discovered it in 1965, though they didn't know what they had at first. They detected a faint microwave hiss coming from every direction in the sky. Same temperature, same intensity. Didn't matter where the antenna pointed. They initially blamed pigeons nesting in the equipment, cleaned the antenna, signal unchanged. What they had detected was the cosmic microwave background, the afterglow of the early universe. Released 380,000 years after the Big Bang, now cooled to just 2.7 degrees above absolute zero. Coming from everywhere equally, because the early universe surrounded Earth in every direction equally, because there is no special location, no preferred direction, no address in the cosmos that is the middle. This property isotropy has been verified by surveys counting millions of galaxies across hundreds of millions of light years. But here's the implication that takes a moment to land. The universe doesn't have a center at all. An infinite space without a center is also an infinite space without an edge in any conventional sense. A center and an edge are geometrically linked. Remove the center, and the edge loses its referent. Edge of what? Edge relative to where? This is what makes the question, where does the universe end, so structurally strange. And here's what makes it stranger. The same measurements that suggest the universe is very likely infinite cannot actually confirm it. They confirm that if there's an edge, it's far beyond anything measurable. The universe could be very large and finite, or genuinely, mathematically infinite. The evidence cannot currently separate them. But before we can go deeper into that, the oldest light in the universe has a secret, and it rewrites what we think the CMB actually is. The oldest light in the universe reached us in 1965. We received it as noise from an antenna pointed at nothing in particular, but it did not begin as noise. 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the early universe was opaque. Photons couldn't travel more than a short distance before scattering. The universe was a glowing fog, impenetrable to light. Then the fog lifted, the light trapped in the plasma finally scattered outward, in all directions simultaneously. It has been traveling ever since. It has traveled for 13.8 billion years. The space it has crossed has expanded by a factor of roughly 1100. The light itself was stretched, its wavelength lengthened 1100-fold, cooling from 3000 degrees Kelvin to 2.725. What was once visible light is now microwave radiation. This is the CMB. But here's what most representations get wrong. The CMB is not a wall. It is not a surface you could reach if you traveled far enough. It is a time, not a location. Travel toward the CMB, and the CMB moves with you. The surface is always as far away as the horizon, because the CMB and the horizon are the same thing. You cannot reach the past, but the CMB contains a specific number that changes the scale of this entire question. The plasma that released the CMB photons we detect tonight at the moment of recombination, it was roughly 42 million co-moving light years from what would become Earth. Inflation then stretched that region by a factor of 10 to the power of 26. 10 to the power of 26. That number has no analogy. A region smaller than a proton became larger than a galaxy in 100 millionth of a trillionth of a second. But the same inflation happened everywhere. Every region of the pre-inflationary universe was stretched by the same factor. And here is what that means. The CMB we detect is not the CMB detectable from the Andromeda galaxy. Their sphere of last scattering is the same size, centered on them, offset from ours. Both spheres are sampling from the same underlying universe, an underlying universe that, by the best current measurements, is effectively infinite. And somewhere in that infinite volume, right now, there are regions whose light is just leaving. regions whose current state we will receive in 46.5 billion years, if anything is still here to receive it. The oldest thing we can see is not the oldest thing that exists. Not even close. In the first 10 to the power of negative 32 seconds after the Big Bang, the universe didn't just expand, it detonated. Not like a fireball into empty space, there was no empty space outside it. Space itself expanded. A region smaller than a proton became larger than a galaxy. This is cosmic inflation, first proposed by Alan Guth in 1980. And the evidence for it is written across the CMB in a specific, testable way. The temperature fluctuations in the background radiation, those tiny variations of 1 part in 100,000, are scale invariant. They have the same statistical properties at all size scales. That's exactly what inflation predicts. Quantum fluctuations stretched to cosmic scales. But here's the problem inflation creates. Most models of inflation don't stop. They describe a process that ends locally in pockets, in bubbles, but continues globally. In some regions, the inflaton field decays, and a hot Big Bang follows. In others, quantum fluctuations keep the field high enough that inflation continues. Those regions keep expanding exponentially. Inflation doesn't end globally. It ends in patches. Our observable universe is one such patch. One bubble among a potentially infinite cascade of bubbles, each too far from the others to ever communicate. The space between them is expanding faster than any signal could cross it. And this bubble, our bubble, was stretched by inflation to a size at least 10 to the power of 23 times larger than what we can observe. 10 to the power of 23. That's larger than the number of atoms in every star in the observable universe. The observable universe is not a sample of the whole. It is more like a single atom sampled from a star. But that assumes minimum inflation. Most models don't produce minimum inflation. Most models produce something closer to the only honest answer left: infinity. And that infinity has a geometry. And the geometry has a measurement. And the measurement produced a number that should not exist. Space can be curved, not as a metaphor, as a measurable physical property of three-dimensional space. General relativity tells us that the overall geometry of the universe is determined by its total energy density. There are exactly 3 possibilities. Too much energy density. Space curves positively, like the surface of a sphere. Parallel lines eventually meet. The universe is finite. Travel far enough in one direction and you return to where you started. Too little. Space curves negatively, like a saddle. Parallel lines diverge. The universe is infinite. Exactly critical density. Space is flat. Parallel lines stay parallel forever. Euclidean geometry holds everywhere, at all scales. In 2018, the Planck satellite released its final CMB measurements with the highest precision ever achieved. The curvature parameter, the deviation from perfect flatness, was measured at 0.001, with an uncertainty of plus or minus 0.002. Consistent with 0, not approximately 0, 0 within measurement precision. The universe is flat, and here is what nobody prepares you for. To be flat today, the universe had to be flat at the beginning to within 1 part in 10 to the 60th. 1 part in 10 to the 60th. If the initial density had deviated by that much, 1 part in 10 to the 60th, the universe would either have collapsed within the first, second, or expanded so fast that no structure could ever form. That precision is not natural. That precision is what inflation predicts it. Naturally drives curvature towards 0, regardless of initial conditions. The way inflating a balloon drives its surface toward flatness. And a flat universe, in every model that fits the data, is an infinite universe. Not proven, but implied, strongly, by the most precise measurement in the history of cosmology. Now here's what flat geometry combined with inflation produces: a consequence so large that cosmologists argue about whether it even belongs in science. Here is something that sounds physically impossible. The galaxies at the edge of the observable universe are receding from us faster than the speed of light, not approaching the speed of light. The most distant galaxies we can observe are moving away at several times the speed of light. And no law of physics is being violated. The confusion comes from conflating two different things: the speed of objects through space and the speed of space itself expanding. Einstein's special relativity limits the first. No object can move through space faster than light. But there is no limit on how fast space can expand. Space is not an object. What this means in practice: pick any 2 points more than about 14 billion light-years apart, and the space between them is expanding at a rate that carries them apart faster than light. Every galaxy beyond roughly 14 billion light-years is receding from us faster than light right now. And yet, we can still see some of them, because the photons reaching us tonight left those galaxies long ago when they were closer. The photons were already on their way before the galaxy crossed the 14 billion light-year threshold. Once a photon is close enough, it can outrun the expansion. But for galaxies beyond 46.5 billion light-years, the edge of the observable universe, even this doesn't work. Photons released at any time from those regions cannot make progress toward us. They are being carried away faster than they travel. The universe beyond our horizon is, by the physics of light and expansion, permanently invisible. Not because of technology, because of geometry. And here is what makes this personal. The cosmological horizon, that invisible boundary, has been shrinking in one specific sense for 5 billion years. Not in radius, in what it contains, because dark energy is accelerating the expansion. More and more galaxies cross the threshold where their future light can never reach us. The event horizon for future communication is currently about 16 billion light-years. Every galaxy beyond that distance is already gone from our future. Their ancient light will keep arriving for a while, but nothing they do from now on will ever reach us. We are already in a universe where most of what exists is permanently unreachable, and it was a specific discovery, unexpected, initially rejected by the people who made it, that told us the separation is accelerating. 5 billion years ago, a force began to dominate the universe. It has no name that fully captures what it is. Dark energy is what we call it, whether it is a property of empty space itself, a new field, or something else entirely genuinely unknown. What is known is its effect. The expansion of the universe is accelerating, not just continuing, accelerating. This was discovered in 1998 by 2 independent teams studying distant Type Ia supernovae, Saul Perlmutter's group and Brian Schmidt and Adam Rees's group, both expected to measure how much the expansion was slowing down due to gravity. Instead, they found the opposite. The supernovae were dimmer than expected. Dimmer meant farther than a decelerating universe would place them. The expansion is speeding up. The result won 3 physicists the Nobel Prize in 2011, and it has a long-term consequence that takes some time to sit with. At the current rate of acceleration, galaxies beyond our local group are already receding faster than light. In roughly 100 billion years, every galaxy outside the local group will have been carried so far beyond the cosmological horizon that not a single future photon from any of them can reach us. The sky, seen from Earth at that time, will show only the Milky Way and its bound companions. The rest of the universe, 2 trillion galaxies, or more, or infinitely many, will be invisible. Not dim, gone. And here's the specific mechanism that makes this permanent. The photons that fill our sky tonight, the ancient light from distant galaxies, the CMB, the spectral signatures of 2 trillion galactic histories, those photons are already on their way. They'll keep arriving for a while yet. We'll use them, observe them, analyze them, but no future photon from those galaxies will follow. The information we're receiving now is the last information we'll ever receive from most of the observable universe. And in 100 billion years, whatever exists here will look out at an apparently small, finite, isolated island of stars with no evidence whatsoever that a larger universe ever existed. They won't. And here's where the Olbers paradox comes in, because the darkness between the stars tonight is telling us something most people never realize it's saying. Heinrich Wilhelm Olbers asked the question in 1823. If the universe is infinite and filled with stars, why is the night sky dark? An infinite universe with infinite stars should fill every line of sight. No matter which direction you look, trace that line far enough and it should hit a stellar surface. The sky should be as bright as the surface of a star everywhere, always. It isn't. That darkness is evidence. The resolution came in the 20th century. The universe had a beginning. It is only 13.8 billion years old. Stars have been shining for some fraction of that time. The universe hasn't existed long enough for every line of sight to fill with starlight. We see darkness between the stars not because the universe is finite in space, because it is finite in time. But here's the part that matters for tonight's question. The dark sky is consistent with a universe that is either spatially finite or spatially infinite as long as it has a finite age. An infinitely large universe that began 13.8 billion years ago would look exactly as dark at night as the universe we observe. The finite age does all the work. Spatial infinity leaves no fingerprint in the darkness. So when you look up tonight and see the dark between the stars, you're not seeing evidence of a small universe. You're seeing evidence of a young one, a universe that began and hasn't yet had time to fill. What that universe's full spatial extent actually is that question. The darkness cannot answer, but the geometry might be able to, except the geometry leads somewhere stranger than an edge. There is a possibility cosmologists take seriously that the observable universe gives us no way to rule out, and that would redefine infinite entirely. The universe might have a topology. Topology is the study of how a space connects to itself globally, independent of its local geometry. And flat geometry zero curvature doesn't uniquely determine topology. But you can also have a flat, finite space that wraps around itself the way a video game screen wraps, cross the right edge and appear at the left, with no wall, no seam, no indication you've crossed anything. In this scenario, travel far enough in one direction and you return to where you started. The universe wouldn't end. It would loop. In a sufficiently small torus universe, you could detect it. Duplicate images of distant galaxies would appear in multiple parts of the sky, the same structure visible from multiple directions at different look-back times. Cosmologists searched for this signature in the Planck CMB data. They found no evidence, but that only rules out topologies where the repeating unit is smaller than the observable universe. If the universe loops on a scale larger than what we can observe, we would never know. The flatness measurements would be unchanged. The CMB would look the same. The galaxy distribution would be indistinguishable from an infinite universe. Every scenario consistent with current data allows the universe to be either finite or infinite. The data doesn't choose, and this is the wall the question, where does the universe end, keeps hitting. The answer may exist, but it is permanently on the other side of an information horizon that physics itself enforces. We can get closer to the edge. We cannot get past it. But something is on the other side, and something enormous is pulling everything toward a specific point in the sky, and we still can't fully identify what. There is something behind the plane of the Milky Way that is pulling our entire galaxy, and the Andromeda galaxy, and the entire Virgo supercluster, all of us toward a single point in the sky. It is called the Great Attractor. Its existence was inferred in 1973 by astronomers, measuring peculiar velocities, the motion of galaxies relative to the overall expansion. The local group is not simply expanding away from everything else. It is also moving. At roughly 600 kilometers per second, toward a specific direction in the constellation Centaurus. Something massive is there, pulling. For decades, its identity was obscured by the zone of avoidance, the region of sky blocked by the disk of the Milky Way itself, where dust and gas prevent optical observation. We were being pulled towards something we literally could not see. In 1986, a team known as the Seven Samurai astronomers, Burstein, Davies, Faber, Lynden-Bell, Terlevich, Wegener, and Dressler mapped the velocities of more than 400 elliptical galaxies and confirmed the flow was real. Something with the gravitational influence of tens of thousands of galaxies was drawing everything in this region of space toward a single location, roughly 250 million light-years away. Later, radio and X-ray observations revealed the Norma cluster at the approximate location. Then, in 2016, the Vela supercluster was mapped behind it, extending across more than 800 million light-years, discovered by René Kraan-Korteweg's team at the University of Cape Town. But even accounting for the Norma cluster and Vela supercluster, the gravitational pull doesn't fully add up. Something else might be there, something further. We are falling toward an incompletely identified mass at 600 kilometers per second, and the identification isn't finished. In an infinite universe, the Great Attractor is not exceptional. Its mass is enormous by human standards, but by the standards of an infinite universe, it is one gravitational anomaly among infinitely many, each pulling its region of space in its particular direction, each embedded in a web of structure extending in every direction without end. And that web, the cosmic web, has something strange about its largest known structure, something that may or may not be allowed to exist. The largest known structure in the observable universe stretches roughly 10 billion light-years across. The Hercules Corona Borealis Great Wall. Found in 2013 when astronomers mapping gamma-ray burst distributions noticed a statistical excess far too large to be coincidence. 10 billion light-years. The observable universe is 93 billion light-years across. This structure spans more than 1/10 of everything we can observe. Here is the problem. The cosmological principle, the same principle that tells us no location is special, verified by galaxy surveys and CMB measurements, predicts the universe should be smooth on scales above roughly 1 billion light-years. No structures. No patterns larger than about 1 billion light-years across. The Hercules Corona Borealis Great Wall is 10 times that limit. It either violates the cosmological principle, or it's a measurement artifact gamma-ray bursts may not trace the underlying matter distribution faithfully. Future surveys may resolve it, but until they do, the largest structure we know about may not be permitted to exist. And in an infinite universe, there is no upper limit on how large a structure can be. Inflation produces density fluctuations on all scales. On scales beyond the observable region, those fluctuations could produce structures that dwarf the Hercules Corona Borealis wall by orders of magnitude. We have no way to look for them. They're beyond the horizon. What we do know is that the cosmic web, the filaments and voids that fill the observable universe, does not end at the horizon. It continues. By the cosmological principle, the same pattern repeats and extends on and on, beyond the observable boundary, into regions we will never see. There is no edge to the cosmic web in an infinite universe, and most of that web is emptier than you imagine. Most of the universe, by volume, is empty, not the emptiness of intergalactic space, which contains a few atoms per cubic meter, threaded by magnetic fields and cosmic rays. The emptiness of voids, regions hundreds of millions of light-years across where the density of matter is so low that even by the sparse standards of the cosmos, they qualify as almost nothing. The largest known void is the Boötes void, discovered in 1981 by Robert Kirshner's group during a galaxy redshift survey. It stretches approximately 330 million light-years across. It contains roughly 60 galaxies. In that same volume of typical cosmic space, you'd expect several thousand. 60. The gravitational pull of surrounding clusters drained matter outward for billions of years. The interior emptied. The void grew. It is still growing now, as dark energy accelerates the expansion of every cubic meter within it. By volume, the observable universe is 60 to 70% void. The matter, all the stars, galaxies, clusters, everything luminous occupies the remaining 30 to 40%, concentrated in thin sheets and filaments, the edges of those soap bubble voids. The universe, structurally, is almost nothing punctuated by extremely thin membranes of something. And here's the specific consequence for the question of infinity. In an infinite universe, there are infinitely many voids, all following the same physics, organized by the same forces, extending without limit in every direction. The cosmic web has no edge, but what fills the space inside those voids, what space itself is made of when nothing else is there, is stranger than the structure around it. Between every galaxy, between every star, between every atom, space is not empty. Every particle you know, electron, photon, quark, is an excitation of a field that permeates all of space. The electromagnetic field exists everywhere. The electron field exists everywhere. The Higgs field exists everywhere. Space is not the absence of things. It is the substrate in which all things exist. And these fields, even in their lowest energy state, the vacuum are not still. Quantum mechanics requires that a field cannot simultaneously have a precisely zero value and a precisely zero rate of change. This is the Heisenberg uncertainty principle applied to fields. The consequence, even in the emptiest possible space, fields fluctuate continuously, randomly, spontaneously. These are vacuum fluctuations. They are real. They have been measured. The Casimir effect, first predicted in 1948 by Hendrik Casimir and measured in 1997 by Steve Lamoureux, demonstrates them directly. Place two uncharged, perfectly conducting plates very close together in vacuum. The quantum fluctuations between the plates are constrained, only certain wavelengths fit in the gap. Outside the plates, all fluctuations are permitted. The result, a pressure imbalance pushes the plates together. A measurable, real force from nothing. Vacuum energy is real. And here's where it connects to the question of infinity. The vacuum energy of quantum fields contributes to the expansion of space exactly as dark energy does. In fact, the leading candidate for what dark energy actually is vacuum energy, the energy of quantum fields in their lowest state. The problem: the theoretical calculation of that energy gives a result roughly 10 to the power of 120 times larger than the observed value of dark energy. 10 to the 120. That is the worst confirmed prediction in the history of physics. The theoretical and observed values differ by 120 orders of magnitude. This discrepancy is not understood. Its resolution may require entirely new physics. And whatever resolves, it will also tell us something about the structure of space at the larger scales. The void is not void. The emptiness has energy, and the energy doesn't match what the theory predicts. That mismatch is one of the deepest unsolved problems in physics. And we'll come back to what it might mean, because the answer could change whether the universe is infinite at all. 27% of the total energy content of the universe is matter we cannot see, touch, or directly detect. We know it exists because of what it does. Fritz Zwicky noticed it first, in 1933. Measuring the velocities of galaxies in the Coma cluster, he found they were moving too fast. The visible mass, all the stars, all the gas was insufficient to provide the gravity needed to keep those galaxies from flying apart. Something invisible was adding mass. He called it Dunkel materia, dark matter. The result was largely ignored for 40 years. Then Vera Rubin and Kent Ford began mapping the rotation curves of spiral galaxies in the 1,970 seconds. Stars at the outer edges of galaxies should orbit more slowly than stars near the center, just as Neptune orbits the Sun more slowly than Mercury. The rotation curves should fall off with distance. They didn't. The curves were flat. Stars at the outer edges orbited just as fast as stars near the center, only possible if there was far more mass in the outer regions than any visible matter could explain. Enormous invisible halos of matter extended far beyond the visible disk of every galaxy they examined. The halos are dark matter. Whatever it is, it doesn't emit light, doesn't absorb light, doesn't interact with ordinary matter except through gravity. And without it, nothing we can see would exist. Dark matter clumped first in the early universe because it didn't interact with the plasma that kept ordinary matter hot and uniform. Dark matter formed halos first. Ordinary matter fell into those halos. Galaxies condensed at their centers. Without dark matter, there are no galaxies. Without galaxies, there are no stars. Without stars, there is no you. In an infinite universe, dark matter extends infinitely as well, the invisible skeleton on which all visible structure is built, tracing the cosmic web across a volume we cannot fully observe, governing the distribution of galaxies across scales we cannot reach. And we still don't know what it is. Every proposed particle, weakly interacting massive particles, axions, primordial black holes, has been searched for without confirmed detection. Every proposed candidate has been constrained. Nothing has been caught. The majority of the matter in the universe is unknown. In an infinite universe, that means an infinite amount of unknown matter, structured in ways we are still mapping, pulling on everything, including the local group at 600 kilometers per second, towards something we can't fully see. The Great Attractor, the dark matter web, the quantum vacuum, all pulling at the question of the universe's extent from different directions. And then there is the future, which is where the question gets its most specific answer, because the future of the observable universe has a timeline, and the timeline ends in a specific way. This is not speculation. The timeline is precise. In approximately 150 billion years, 10 times the current age of the universe, the Milky Way and Andromeda will have merged. The local group will have settled into a single large elliptical galaxy, gravitationally bound. Dark energy too weak at these scales to unbind it. The cluster will survive. Everything beyond it will be gone. Not faded, not dim. Gone. The last photons from distant galaxies will have arrived. The galaxies will have crossed the cosmological event horizon. Their future light will stay with them permanently out of reach. An astronomer in that era will look out and see nothing beyond the local group. The CMB will have cooled to a temperature indistinguishable from quantum noise. The large-scale structure we map today, the cosmic web, the voids, the clusters, will be invisible. No distant galaxies to survey, no recessional redshift to measure, no spectral data from 2 trillion galactic histories. The evidence for the Big Bang will be gone. If those future observers reconstruct cosmology from scratch, what do they conclude? A small, finite, isolated island of matter in apparent emptiness. Stars of various ages, no evidence of expansion, no evidence of anything beyond. They would be wrong, and they would have no way to know it. Every piece of observational evidence we have tonight, the expansion rate, the CMB, the large-scale structure, the existence of 2 trillion observable galaxies, all of it will be locked behind the event horizon in 100 billion years, carried away with the galaxies that hosted it. What we know tonight, those future observers cannot know, but only because we are early, and that's the specific reversal hiding in the question of the infinite universe. The fact that the universe is infinite doesn't make its observable record permanent. The larger the universe, the more certain it is that most of its history is inaccessible. Infinity guarantees not abundance of knowledge, but abundance of permanent unknowns. And there's one unknowable that takes the longest to sit with. In 1543, Copernicus proposed Earth was not the center of the universe. The Sun was. He was partially right. The Sun is not the center either. The Sun orbits the Milky Way. The Milky Way is one galaxy among 2 trillion in the observable universe. No location is more central than any other. This is the Copernican principle. We are not in a special place. Applied to an infinite universe, the consequence goes somewhere most people are not prepared to follow, because an infinite universe with the same physics everywhere means every physically possible configuration of matter occurs, and occurs infinitely many times. This is not a metaphor. It's the direct mathematical consequence of combining infinity with a finite number of possible configurations. The observable universe contains roughly 10 to the power of 80 atoms. The number of possible arrangements of those atoms is enormous but finite. Any finite number of possible arrangements, repeated across an infinite universe, means every arrangement occurs. Including this one, a planet orbiting a star, with beings lying in the dark wondering about the extent of space. This specific configuration of matter exists not here and nowhere else. It exists infinitely many times. The nearest such copy, by probability calculations based on matter, density and volume, is at a distance of approximately 10 to the power of 10 to the power of 29 meters. That number has no everyday comparison, but it is a finite distance in an infinite universe. And that region is not approximately similar to this one. It is indistinguishable. Every version of tonight that could ever happen is happening infinitely many times in an infinite universe. There's no way to prove it. The copies are beyond the event horizon. They will always be beyond the event horizon. But the mathematics doesn't ask for permission. Henri Poincaré proved in 1890 that a finite mechanical system with conserved energy will, given enough time, return arbitrarily close to any previous state. In an infinite universe with an infinite future, the consequence is stranger. In the extremely distant future, on timescales written as 10 to the power of 10, to the power of some large number, all stars will have burned out. All black holes will have evaporated via Hawking radiation, a process itself requiring perhaps 10 to the power of 100 years for the largest black holes. The matter that remains will be cold, dispersed, near maximum entropy. But quantum fluctuations don't stop. Over timescales that make the current age of the universe look like a single Planck time, quantum fluctuations will spontaneously create any configuration of matter, including configurations as organized and specific as a living brain, or a planet, or a galaxy. The probability is nearly zero, but nearly 0 times infinite time is not 0. It is 1, and then it happens again. In an infinite universe, with an infinite future, every configuration of matter will occur, including this one, including you, lying still, in the dark, somewhere between 13.8 billion years after the Big Bang and the first recurrence. The physics doesn't tell us when that first recurrence is. The timescales are genuinely unimaginable, but in an infinite universe, they are certain, and you are at an unknown position within the sequence. Here is where we have to be precise. The word infinite does 2 different things in 2 different contexts, and conflating them is one of the most common mistakes in popular cosmology. Mathematical infinity is a formal concept. It is the cardinality of the set of natural numbers. It comes in different sizes. Georg Cantor showed in 1891 that the infinity of real numbers is strictly larger than the infinity of natural numbers, using his diagonal argument. Mathematical infinity is well defined, rigorously treated, manipulated with precision. Physical infinity is a claim about the universe. It says the actual extent of space is literally without bound. The number of particles is infinite in the mathematical sense. These are not the same thing. The measurements suggesting the universe is flat are consistent with infinite extent. They do not prove infinite extent. A very large finite universe with undetectable curvature would produce the same measurements. No instrument we have, or could, in principle have, would distinguish them. And physical infinity raises real conceptual problems that mathematical infinity doesn't. If the universe is physically infinite, there are actually infinitely many particles, infinitely many photons, infinitely many configurations occurring simultaneously. This creates what physicists call the measure problem. Every event that can happen happens infinitely many times. Calculating the probability of any outcome requires counting and comparing infinities. But different counting methods give different answers. The same physical setup produces different predictions depending on mathematical choices that should be irrelevant. The measure problem is unsolved. It is one of the reasons some physicists argue that eternal inflation, as usually formulated, is not a proper scientific theory. It predicts everything and therefore predicts nothing. None of this means the universe is definitely finite. It means the question is harder than it appears, and the word infinite carries more weight when applied to physical reality than it does on a blackboard. What the measurements tell us: the universe is either infinite or very large. What they cannot tell us: which one. Here is the epistemological trap at the center of this entire question. Every measurement we can make is a measurement made from inside the observable universe. Every instrument, every photon, every gravitational wave, all of it from within the sphere centered on Earth. 46.5 billion light-years in radius. We have no tool that accesses information from outside that sphere. Not because of current technology, because of physics. Information from outside the observable universe cannot reach us. What this means for where does the universe end is exact. If the edge of the universe is beyond the observable horizon, we cannot detect it. Any edge, any curvature, any topology, if it operates on scales larger than the observable universe, it is observationally inaccessible, permanently. This is called the problem of underdetermination. Multiple theories make the same predictions within the observable region. No measurement can distinguish between them. An infinite flat universe and a very large finite universe with undetectable curvature are empirically equivalent, not approximately equivalent. Identical in all observable predictions, the distinction between them is real. It is just unresolvable. Some physicists are comfortable with this. Unresolvable questions are not unique to cosmology. There are mathematical questions that cannot be proven within standard axiom systems. The universe may have features that are real but unknowable. Others argue that a question with no possible empirical resolution is metaphysics, not physics. That cosmology should restrict itself to claims that could in principle be tested. The argument has been going on for decades. What has been established is the boundary. We know what we can know, we know what we cannot. And the line between them is the cosmological horizon, sharp, physical, and final. There is a scale at which the concept of smooth, continuous space may stop making sense. The Planck length, approximately 1.6 times 10 to the power of negative 35 meters, about 20 orders of magnitude smaller than a proton, is where quantum gravitational effects are expected to become significant. At this scale, the smooth geometry of general relativity and the probabilistic nature of quantum mechanics cannot be treated separately. What happens there, nobody knows. Loop quantum gravity suggests space itself is quantized at the Planck scale, a minimum distance below which distance loses meaning. Space, in this picture, is not infinitely divisible. It is composed of discrete units. If correct, an infinite universe built of discrete Planck length units would be infinite in count, but not infinitely divisible. That infinity is different from the smooth, geometric infinity assumed by the flat space models. String theory suggests something else entirely. Additional compactified dimensions at the Planck scale, curled so small as to be undetectable at everyday scales, determining the physical constants of the universe we observe. Neither has been confirmed by experiment. The Planck scale is inaccessible to any current or foreseeable accelerator. Probing it would require energies roughly 10 million billion times the maximum energy of the Large Hadron Collider. But the question of what space is at the smallest scale is directly relevant to what space is at the largest. If space is discrete, if there is a minimum length, the question of infinity changes. Two infinities that are not the same, and if the structure of space at the Planck scale is governed by physics we haven't discovered, then every extrapolation of current geometry, including the extrapolation that flat space means infinite space, is potentially incomplete. We are reasoning about the largest scales from measurements that tell us nothing about the smallest. At the smallest scales, physics may be doing something we haven't found yet. Here is where we come back to the beginning. You are at the center of the observable universe. You are also at the boundary of your own causal horizon, the limit of where anything you do tonight can ever have an effect. Nothing you cause can propagate faster than light. The sphere of your influence is growing at the speed of light. It will grow forever. But the universe, you can see the sphere of information that has already reached you, is also a horizon. The limit of what had time to arrive. You are not at the edge of the universe, but in a meaningful sense, you are always at the edge of what you can know. And the part of the universe you're inside your observable sphere is unique to you, in the sense that it is centered on you. It overlaps with the spheres of everyone near you. But it is a different sphere from that of an observer in Andromeda, or in a galaxy a billion light-years away. Each observer is sampling from a different region of the universe's history. The light reaching you right now, across 46.5 billion light-years, comes from a universe that is, in the best models, infinite or very nearly so. The sphere you inhabit is a bubble in a space that does not end. The boundary of your observable universe is not a wall beyond which the universe fails. It is a horizon. And beyond every horizon, the universe continues carrying its galaxies, its voids, its dark matter and dark energy, its quantum fields humming in the vacuum, its Planck-scale structure we haven't yet understood, its stars burning in configurations we will never see, its possible observers looking up at their own finite windows into an infinite dark. You have been lying in the dark tonight at the center of a sphere of light that extends to the edge of observable time. The universe goes further. It always has. In roughly 100 billion years, an astronomer in the merged local group will look out and see nothing. Not a depleted universe. Nothing beyond the stars of their own cluster. Every other galaxy will have crossed the event horizon. The CMB will have cooled below any detection threshold. The recessional redshift that demonstrates expansion will have no distant galaxies to demonstrate it. Those astronomers, if any exist, will have no observational evidence for the Big Bang, no evidence for anything beyond their own cluster. The universe, from their vantage point, will appear small, finite. The local group, roughly 100 billion stars, concentrated in a region a few million light-years across, will be all that is accessible. If they reconstruct cosmology from scratch, what do they conclude? A finite island of matter in empty space, stars of various ages, no recessional redshift, no CMB, no evidence for inflation, dark energy, or the structure of the cosmic web. They would be wrong, and they would have no way to know. The information required to reconstruct the true history and extent of the universe will have left their observable region, carried away by accelerating expansion, locked behind an event horizon that cannot be crossed. We know what they cannot know, but only because we are early, and here's what this means for us. What are we missing right now that an earlier observer would have known? What evidence for the true nature of the universe was visible in the early cosmos and has since been carried away from us? What did the universe look like before the information we've already lost was gone? We don't know. We can't know. That evidence is gone. The window of cosmic knowledge is open now. It will not always be. Every photon that has ever reached your eye carried news from the past, not history. The past itself, a moment that no longer exists, transmitted by light that left its source before you opened your eyes. Sirius is a picture of Sirius as it was 8.5 years ago. Andromeda is how Andromeda looked 2.5 million years ago, when early humans were learning to walk upright. The faint smear of the Virgo cluster carries an image from 53 million years ago, when non-avian dinosaurs had been gone for only 11 million years. The further you look, the deeper into the past you see. At the edge of the observable universe, you are looking at matter as it existed 13.8 billion years ago. Matter that has since evolved into galaxies, burned through generations of stars, scattered its metals, and perhaps on some planets produced observers who are themselves looking back through their own horizon. You will never see what that matter looks like now. The present state of the universe is invisible. What you see is always the past. This compounds the horizon question in a specific way. When you ask what lies beyond the edge, you're already asking about a present you cannot see. The matter at the edge exists right now in some configuration that has had 13.8 billion years to evolve from the hot plasma you see in the CMB. It has had 13.8 billion years of gravity, fusion, radiation pressure, dark energy, and slow stellar drift to produce whatever it is right now. You will never see it. Not because it doesn't exist, because the light that would carry its image to you is just leaving now. It will arrive in 46.5 billion years, if anything is still here to receive it. The night sky is a museum. Everything on display is already over. We've been circling it all night. Where does the universe end? Sounds simple. It is a stack of questions, each requiring a different framework, each bumping against a different limit. Does the observable universe have an edge? Yes. 46.5 billion light-years in every direction, defined by light, travel time, and expansion. Real, physical, computable. Does the physical universe have an edge? Unknown. The curvature measurements are consistent with zero. Zero curvature is consistent with infinite extent, but consistent with is not proven. The universe might be finite with a characteristic scale large enough to be undetectable. Does the inflationary multiverse have an edge? By the mathematics of eternal inflation, no. But the multiverse is not directly observable. Its structure is inferred, not measured. Can we ever answer any of these? The first is answered. The second may be permanently unanswerable. Any evidence for finitude would need to come from scales larger than the observable universe, which we cannot access. The third may never be testable. And there is a fourth question hidden inside all of these. What does end mean? A finite universe without boundary, like the surface of a sphere in 3 dimensions, doesn't end in any ordinary sense. Travel in one direction indefinitely, and you return to your starting point. No wall, no seam. The space is finite, but has no edge. A finite universe with a hard edge where space simply stops is disfavored by almost every physical model, because the boundary requires a physical explanation no current theory can provide. What is on the other side of a hard edge of space? What happens to a particle that reaches it? Physics has no answer, and an infinite universe doesn't end by definition. So the answer to where does the universe end is, at its most precise, the universe, as we understand it, in every model that fits the data, does not end in any direction, at any distance. It continues in observable form to 46.5 billion light-years, in physical form to at minimum 250 times that, and by the best supported models, without limit. The horizon is not the end. The CMB is not the end. The edge of visibility is not the end of space. And the end of space, if there is one, is beyond anything we can reach, measure, or infer. Tonight, we can hold that. The universe does not fit in an answer. It barely fits in a night. When you were born, the observable universe was slightly smaller than it is now. Not by much, a matter of years of additional light travel time. A thin, additional shell of previously invisible space, but smaller. And the day you die, the observable universe will be slightly larger than tonight. more ancient light will have arrived. More of the distant universe will have crept into visibility. We are growing our knowledge of the universe simply by waiting. But we are also losing it. Galaxies drifting beyond the event horizon, their future light failing to arrive, the cosmic record that exists tonight becoming unavailable. This is the condition of knowing in a universe like ours. The horizon is always present. The limit of what can be known is always nearby. And yet within that limit, within the sphere of observable space that surrounds you, there is everything. 2 trillion galaxies, 10 billion years of stellar evolution recorded in spectra, the echo of the Big Bang still detectable in the background radiation, the geometry of space measured to 4 decimal places, the age of the universe known to within 100 million years. Within the horizon, there is abundance. The abundance doesn't extend to everything. Some questions have no answers available to us. Some features of the universe are locked behind the cosmological horizon and will never send us information. Some questions whether the universe is truly infinite, whether it loops, what lies at the Planck scale may never be resolved. These are not failures of science. They are properties of the universe, the way it is structured, the way information travels within it, the way expansion creates permanent boundaries between regions. The universe has limits on what it will reveal, and within those limits, what it has revealed is extraordinary. The fact that you are at the center of your observable sphere, the fact that every observer is, the fact that there is no special location, the fact that the universe, in every direction, at every scale, follows the same physics and produces the same structures, the fact that it began and has been expanding for 13.8 billion years and shows no sign of stopping. The universe began moving and it has not stopped since. Neither have you. There is one direction in which you cannot look into the past. Down. The Earth's interior blocks any direct optical observation, but beyond that specific obstacle, something more fundamental limits what can be seen in any direction. You can only see what light can carry, and light can only carry what it was allowed to escape. The universe before recombination, before the fog lifted 380,000 years after the Big Bang, is invisible to any optical, infrared, or radio telescope. Light could not travel freely in that era. Nothing from before recombination carries a photon signal that can reach us today, but it carries other signals. Gravitational waves ripples in space-time, first detected in 2015 by the LIGO experiment, interact so weakly with matter that they travel essentially unimpeded through the universe. A gravitational wave background from the earliest moments from inflation itself, or from the violent plasma dynamics of the first fractions of a second, would still be traveling today, carrying information from before the CMB. From before the fog, detecting this primordial gravitational wave background is one of the primary goals of the Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030 seconds. If primordial gravitational waves from inflation are found, they would open a window on the universe at a time before any light could escape. Into the first moments, into the era when the physics that set the scale of inflation was being determined. Into the conditions that decided whether the universe would be 250 times the observable region, or 10 to the power of 23 times, or infinite. The universe hid its beginning behind light it refused to emit. It did not hide it from gravity, and gravity does not stop at the horizon. Encerramento. We've traveled tonight from the edge of the observable universe to the Planck scale, from the bubble of space that surrounds you to the infinite continuation beyond every horizon. From the last photon a distant galaxy will ever send us to the far future of a universe still expanding, still cooling, still carrying its quantum fields in the silence between events. What we found was not an edge. We found a horizon. And beyond the horizon, more universe. And beyond that horizon, another. Space continuing in every direction, carrying the same physics, organized by the same forces, structured by the same dark energy and dark matter, for a distance that current science cannot measure. And by the best supported models without limit, the universe you can see tonight is not the universe. It is your share of it. Your window, your 46.5 billion light-year sphere of what has had time to arrive. And within that sphere, if you let it settle the dark outside, the stars is not absence. It is the space between the galaxies. It is the void that makes the structure possible. It is dark energy pressing space apart at every point. It is quantum fields fluctuating in the vacuum. It is the CMB, too cold now to see, too faint to feel, but still there, a whisper from the beginning, still traveling, still filling everything. You are not separate from the space that extends beyond the observable. You are continuous with it. The atoms in your body were formed in stars that live far outside the neighborhood you can observe. The hydrogen at your core was formed in the first minutes after the Big Bang, in a plasma that extended by every current measurement without end. You began in the infinite. You are inside it now. If your eyes feel heavy, let them close. The horizon will still be there when you wake. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. If you're still here, the next journey is already waiting. The universe will still be here when you wake up. So will we. Good night. The first stars in the universe were nothing like the stars you see tonight. They were monsters, formed from pure hydrogen and helium, no heavier elements, no carbon, no oxygen, nothing forged in a stellar interior. Yet these first stars had masses anywhere from 100 to 1,000 times the mass of the Sunday. They burned at temperatures that dwarfed anything in the current universe. They blazed so intensely that they lived for only a few million years. A few million years. The sun has been burning for 4.5 billion. These first stars, called population 3 stars, have never been directly observed. They formed in the first few 100 million years after the Big Bang, in small halos of dark matter, in a universe that was still mostly dark. They burned through their fuel in an eye blink of cosmic time, exploded as supernovae, and seeded the surrounding gas with the first heavy elements carbon, oxygen, iron, silicon that would eventually form planets and, eventually, the atoms in your body. The James Webb Space Telescope has been pushing back toward the era of population 3 stars, detecting galaxies at redshifts above 12, 13, even 15 galaxies that existed within the first few 100 million years of the universe's history. Some show signs of chemical enrichment that may trace back to population 3 supernovae. Some appear more massive than current models predict they should be at that redshift. Something about the early universe's star formation doesn't match the models. In 2023, Webb detected galaxy J ADES GSZ 140 at a redshift corresponding to just 290 million years after the Big Bang. A galaxy already containing hundreds of millions of solar masses of stars. It should not be that massive, that early. Current models of structure formation don't easily account for it. This is not a crisis for cosmology. It is exactly the kind of anomaly that pushes the field forward. But it is a reminder. What we see when we look back toward the first stars is not a confirmed, settled story. It is an active frontier, still being revised. And if the first stars were different from what we expect, heavier, more luminous, more chemically productive, then the history of the universe was different in ways that propagate forward to everything that came after, including you. Every atom heavier than helium in your body was forged in a star and released in a supernova. Some of those atoms trace back to population 3 supernovae. The first explosions in the history of the universe left residue that eventually became you. And in an infinite universe, that process is happening right now in other regions, in other bubble universes, in other galaxies producing other configurations of matter that will, in some distant future, lie in their own dark, wondering about their own origins. The first stars died before the Earth formed. Their residue, is what Earth is made of. And the question of how they formed, how many there were, and exactly when the universe became bright for the first time, that question is still being answered by the best telescope humanity has ever built. The universe you observe tonight is not the universe that has always existed. It is the universe as it has become after 13.8 billion years of transformation so radical that the early cosmos would be unrecognizable. 1 billion years after the Big Bang, the universe looked nothing like it does now. The oldest observed galaxies, some detected by James Webb in 2022 and 2023, with light from redshifts of 12, 13, and beyond, were compact, irregular, furiously star-forming. Galaxy GNZ 11, observed in detail by Webb, existed when the universe was only 430 million years old. It was producing new stars at a rate roughly 25 times higher than the Milky Way does today, packed into a region 10 times smaller. The cosmic star formation rate, the total mass of new stars born per year across the entire observable universe, peaked approximately 10 billion years ago. It has been declining ever since. The universe is past its prime. In stellar terms, most of the stars that will ever form have already formed. The remaining gas reserves are depleted, scattered, ejected by supernovae and quasar winds. The universe is cooling, dimming, settling. In another 10 billion years, new star formation will be a fraction of what it is today. Galaxy clusters will settle into gravitational equilibrium. The remaining gas will be too hot and diffuse to collapse into new stars. We live in a universe in its middle age, not youth, not end a specific moment in a long, slow evolution. Late enough that stable chemistry is possible. Early enough that sun-like stars still burn and new ones still form. A window of perhaps 10 to 12 billion years, during which conditions favor the kind of complexity that asks questions. Before this window, the universe was too chaotic, too hot, too metal poor for complex chemistry. After this window, it will be too cold, too dark, too depleted. We are in the window, and the window, in cosmic terms, is brief. The number 46.5 billion light-years grows with time. Every second, a tiny additional shell of previously invisible universe becomes visible. More ancient light arrives. The observable sphere expands, but the number of galaxies within that sphere is shrinking. Because dark energy is accelerating the expansion, galaxies are crossing the event horizon, the boundary of what can ever reach us in the future, at a continuous rate. Galaxies that cross the event horizon are still observable for a while. Their past light continues to arrive, but no future signal from them will ever reach us. The observable universe expands in radius. The number of observable sources shrinks. Both are true simultaneously. Not paradoxical. The edge of the sphere keeps moving outward, encountering ancient light from galaxies that were always there. Meanwhile, the galaxies already in the observable region are being carried beyond the event horizon, their future signals permanently lost. The visible universe is the most information-rich version it will ever be right now. Tonight, 2 trillion galaxies, 10 billion years of stellar evolution recorded in spectra, the CMB still detectable, gravitational waves from mergers still measurable, the expansion rate still traceable. Tonight is near the peak of astronomical richness. From here, on timescales that make geological time look instantaneous, it diminishes. The observable universe you inhabit tonight is the most complete version any observer in this location will ever have access to. And here's the specific number that anchors this. In roughly 2 trillion years, the total number of stars in all galaxies accessible from the Milky Way will be essentially zero beyond the local group. Not dim, zero. The photons will have arrived. No new ones will follow. 2 trillion years sounds impossibly distant, but the universe is already 13.8 billion years old. 2 trillion is roughly 150 times the current age. In cosmic terms, it is not the end, it is the middle of the beginning of a long, quiet decline. What comes after is not ending. It is patience. In 5 billion years, the Sun will expand into a red giant. It will grow to roughly 200 times its current size, engulfing Mercury, probably Venus, and possibly Earth. The outer layers will drift away as a planetary nebula, a shell of glowing gas expanding into space. The core will collapse into a white dwarf roughly the size of Earth, radiating heat slowly into the void. In about 7 billion years, the Sun will be a cold, dark cinder. This is the standard stellar death for a star like the Sunday. But the universe is full of stars with different fates. Massive stars, those more than 8 to 10 times the Sun's mass, live fast and die violently. They exhaust their fuel in millions of years, collapse, and rebound in supernovae. Their cores become neutron stars, city-sized objects with the mass of the Sun, so dense that a teaspoon of neutron star material would weigh 1 billion tons. Or they collapse further, past any known stopping point, into black holes. Low-mass stars, red dwarfs, the most common type in the universe, burn so slowly they will shine for trillions of years. The smallest red dwarfs will outlive the Sun by a factor of 1,000. Some will still be burning when the universe is 10 trillion years old. In the very far future, after all, the gas that can form stars has been consumed or expelled. The era of star formation ends. The last new star ignites. Then that star burns out, and the universe enters the degenerate era, a vast darkness populated by the cold remnants of stellar evolution. White dwarfs, slowly cooling. Neutron stars, slowly cooling. Black holes, slowly evaporating via Hawking radiation. The evaporation of the largest black holes takes roughly 10 to the power of 100 years. After that, what? Protons may eventually decay on timescales of 10 to the power of 35 to 40 years, depending on which model of particle physics is correct. If protons are stable, the remnants of the degenerate era persist indefinitely. If they decay, all baryonic matter eventually dissolves into radiation and leptons. Either way, what remains is a universe of near maximum entropy, cold, dark, diffuse, and in the far future, host only to the quantum fluctuations that will, given infinite time, spontaneously reassemble into anything that has ever existed. The universe doesn't end. It waits. Here is what is happening to you, right now, as you lie in the dark. The Milky Way is moving at approximately 600 kilometers per second toward the Great Attractor, that incompletely identified mass behind the plane of the galaxy, pulling everything in our region of space in its direction. At the same time, the Earth is orbiting the Sun at roughly 30 kilometers per second. The Sun is orbiting the center of the Milky Way at approximately 230 kilometers per second. The Milky Way is falling toward Andromeda at roughly 110 kilometers per second, and the entire local group is embedded in the Hubble flow, the expansion of space itself, which carries distant galaxies away from us at speeds that increase with distance. At the edge of the observable universe, that recession speed is several times the speed of light. None of this is something you feel. The motion is so vast and the frame of reference so large that there is no sensation, no wind resistance, no vibration. You are moving through the universe at hundreds of kilometers per second in multiple simultaneous directions, and the experience from inside is perfect stillness. But the stillness is the illusion. At every scale, from the orbit of the Earth around the Sun, to the trajectory of the Milky Way toward the Great Attractor, to the expansion of space that carries distant galaxies beyond the horizon, the universe is in motion. Everything is in motion. Nothing in the universe has ever stopped moving since the moment of the Big Bang. Not the galaxies, not the stars, not the atoms in your body, not you. You have never been still. The universe has never permitted it. And the motion isn't slowing down. Dark energy is accelerating every point of space away from every other point. The recession velocities of distant galaxies are increasing. The expansion of space is not approaching an equilibrium, it is approaching an asymptote, a state of faster and faster separation between everything that isn't gravitationally bound together. The universe moves, it has always moved. It will not stop, and you are moving with it at the center of a sphere of observable space toward a destination that no map has yet named. There is a surface you will never reach, no matter how far you travel. Not because it is too distant, because of what it is. The cosmological event horizon, the boundary beyond which no future signal can reach you, is not a location in space. It is a relationship between you and the expansion rate of the universe. As you move, it moves. It is always a specific distance from wherever you are. And that distance is determined not by geography, but by physics, by the current expansion rate, the amount of dark energy, and the speed of light. Try to travel toward the event horizon. Space expands as you travel. The horizon retreats. You move. It moves. You accelerate. It accelerates with you. You can never get there, not because the horizon is running away, but because the horizon is defined relative to you and moves with you. This is different from the observable horizon. The observable horizon is a sphere around you that grows slowly as time passes, as more ancient light arrives. You can't reach it either, because it is in the past. The event horizon is in the future. It is the limit of where you could, in principle, send a signal that would ever arrive. Beyond the event horizon right now, while you lie in the dark, matter exists that will never be in causal contact with you. Not because it is too far to visit, because no signal, not even light, can ever bridge the expanding gap between you and it. The universe is full of things happening that you will never know about, not just because you are here and they are there, because the expansion of space makes the gap uncrossable by any form of information. And those things, whatever they are, matter. They are real. They involve matter, energy, gravity, perhaps life, perhaps questions similar to this one. But they are causally disconnected from you in a way that no future technology will ever change. The geometry of the universe guarantees a permanent limit on what any observer can ever know. And that limit is not failure. That limit is the shape of the universe. When a galaxy crosses the cosmological event horizon, what happens to its information? In classical physics, information is never lost. Every particle carries a record of its history, position, momentum, interaction history. The laws of physics are time reversible. Complete knowledge of any state allows reconstruction of every past state and prediction of every future state. But when matter crosses a horizon, whether a cosmological horizon or a black hole's, the information it carries becomes inaccessible. Not destroyed, perhaps, just unreachable. Stephen Hawking argued in 1974 that black holes slowly evaporate, radiating thermal energy until they vanish. The thermal radiation carries no information about what fell in. The information, he suggested, was destroyed. Quantum mechanics seems to forbid information destruction unitarity. The principle that quantum states evolve in ways that preserve total information is central to the theory. The debate, the black hole information paradox, consumed decades of theoretical physics and remains incompletely resolved. The cosmological horizon raises a similar question, less often discussed. Galaxies receding beyond the event horizon carry with them every record of their existence, every photon emitted by every star, every gravitational wave from every merger, every quantum state of every particle. That information is, from our perspective, permanently inaccessible. Is it lost, or does it persist, encoded in the state of space in a way that could in principle be recovered? The leading view in quantum gravity is that information is never truly lost. It is encoded in subtle correlations in the radiation escaping from horizons, in the quantum state of the vacuum, in structures too fine to detect practically but real in principle. But in principle recoverable and actually recoverable are very different things. In practice, the information of every galaxy beyond the horizon is gone, scattered in quantum correlations too subtle to detect. carried in radiation too faint to measure, preserved by physics but inaccessible by any technology we can conceive. The universe keeps its records. It just doesn't share them with us. In an infinite universe, the volume of information permanently beyond our horizon is infinite. An infinite record of events we will never access, carried by matter, operating on configurations we will never observe. The universe is full of things that happened, and full of things that happened without us. Here is a thought that doesn't get enough attention. The observable universe has been expanding for 13.8 billion years. The observable horizon grows slowly. As time passes every second, a thin new shell of ancient light arrives, and the boundary moves outward by a tiny fraction of a light year. But there is information that was in our observable region and left. Not galaxies that cross the event horizon, those are in our future. Information that existed in the early universe and is no longer accessible because the universe evolved past it. When the universe was 380,000 years old, the CMB photons scattered free. Before that moment, the universe was opaque. The plasma of the early universe interacted so strongly with photons that no light escaped. The only records of that first 380,000 years are the CMB itself, the primordial gravitational wave background, not yet detected, and the abundances of hydrogen and helium in the early universe. Everything else about the first 380,000 years is gone from the photon record. What happened in those 380,000 years? The Big Bang nucleosynthesis, the formation of hydrogen and helium nuclei in the first 3 minutes, the cooling of the universe from inconceivable temperatures to thousands of degrees, the formation of the first atoms. But not only that, if inflation happened, and the evidence strongly suggests it did, the first fraction of a second contained dynamics that set the scale of everything. The size of the universe, the spectrum of the CMB fluctuations, the amount of inflation, the transition to the hot dense state we call the Big Bang. The record of that first fraction of a second is not in any photon. It may be in the primordial gravitational wave background, a background of gravitational waves from the earliest moments, still propagating through the universe, detectable perhaps by LISA in the 2030 seconds. If we detect it, we will be reading a record from before the CMB, from before the fog. If we don't detect it, if inflation produced a gravitational wave signature too weak to measure, then the first moment of the universe may be permanently beyond observational reach, not just beyond the cosmological horizon, beyond any form of detection, and in that case, the most important moment in the history of the universe, the moment that set its size, its geometry, its flatness, will have left no accessible record. We would know it happened. We would not know how. There is a specific kind of discomfort that comes from understanding a question's structure precisely and still not being able to answer it. This is where cosmology leaves us tonight. The question, where does the universe end, is not unanswerable because physics is incomplete. It is unanswerable because the answer, whatever it is, lies outside the region from which we can ever receive information. The physics we have is sufficient to describe the boundary. It is not sufficient to look beyond it. Not because we haven't tried, because the universe is arranged so that looking beyond the cosmological horizon is equivalent to looking outside of time. What lies beyond is real. The matter is there. The galaxies are there. If the universe is infinite, observers are there, perhaps lying in their own dark, asking their own version of this question, finding their own horizon, reaching the same unanswerable edge. What lies beyond is also, in every operational sense, permanently unknown. Scientists are comfortable with permanent uncertainty in a way that is sometimes underappreciated. The unknown is not a failure of the project. It is the project. Each precise answer reveals the shape of the next question more clearly. We know the observable horizon is 46.5 billion light-years. That is known. What lies beyond it is not, and that is also known, specifically. The shape of the ignorance is defined. And defined ignorance is, in its way, a kind of knowledge. You know tonight exactly how far you can see. You know exactly why you cannot see further. You know the physics of the boundary, the history of the expansion, the mathematics of the curvature, the implications of the flatness. You know what it would mean if the universe is infinite, and you know why that cannot be confirmed. That is not nothing. That is what the universe has so far chosen to share, and the sharing isn't finished. The LISA detector will listen for gravitational waves from inflation. Future CMB experiments will constrain the primordial gravitational wave spectrum. Galaxy surveys will push the mapping of large-scale structure to greater precision and greater depth. The observable boundary will yield more of its secrets, year by year. The boundary itself will not move. The horizon remains where physics places it. But within the horizon, the resolution increases. The picture sharpens. The anomalies emerge like the unexpected mass of early galaxies, like the Hercules Corona Borealis Great Wall, like the Great Attractor still resisting a complete identification. And each anomaly is a door, possibly to new physics, possibly to a revised model of inflation, possibly to an understanding of dark matter and dark energy that currently eludes us. The universe does not reveal everything, but it has not stopped revealing. And tonight, lying in the dark, at the center of your observable sphere, you are at the edge of everything that can currently be known and the beginning of everything that cannot. Here is a thought experiment that should unsettle you. Suppose you board a spacecraft tomorrow, the fastest spacecraft ever conceived, one that accelerates continuously at 10 times the force of gravity, approaching the speed of light asymptotically. You aim it at the edge of the observable universe. You press the button. You will never get there. Not because the journey takes too long, not because you'll age out before you arrive, but because the destination is not a place, and even if it were, the edge would always be the same distance from wherever you end up. The horizon is not a location in space that you can approach. It is a relationship between you and light travel time. Move toward it, and it moves with you. The horizon retreats at the same rate you advance, because the edge of the observable universe is defined by how far light has traveled from your current position, and your current position moves with you. There is no place in the universe that is at the edge. Every point in the universe is, simultaneously, at the center of its own observable sphere, 46.5 billion light-years in every direction. And here's the specific consequence that follows from this. Travel at arbitrary speed in any direction for 1 billion years. You arrive in a new location. The observable universe from your new location overlaps with the observable universe from your starting point. The two spheres share most of their volume because 1 billion light-years is a small fraction of 46.5 billion. But your new observable sphere includes regions that your starting sphere did not. You can see ancient light from regions that were behind your own CMB horizon before. And you have lost access to regions that were in your original sphere but that, from your new position, are now beyond 46.5 billion light-years away. The universe you can observe changes as you move. It doesn't grow. It shifts. You trade one slice of the infinite for another. You can never accumulate all slices. The total volume of space, if infinite, contains infinite slices, each subtly different, each centered on a different observer, each containing a different window into the same underlying universe. You will never see the whole. No observer anywhere can. The universe is not hiding from you. It is simply larger than any observation can contain. Human beings have looked up and wondered about the extent of the sky for as long as there have been human beings. The question is not new. The framework for answering it is. For most of human history, the sky was a finite dome, a ceiling above a flat Earth, then a sphere, then a vast space containing the sun and planets, with the fixed stars embedded in a crystalline outer shell. Then gradually, painfully, against centuries of resistance, an infinite void in which the Earth was one rock orbiting one star among many. each expansion of the picture was resisted. Each one turned out to be an underestimate. The Milky Way was thought to be the entire universe until 1924, when Edwin Hubble resolved individual stars in the Andromeda Nebula and confirmed it was a separate galaxy, an island universe of hundreds of billions of stars, separated from the Milky Way by 2.5 million light-years. The universe was suddenly larger by a factor of millions. Then the expansion was discovered, then the CMB, then inflation, then the accelerating expansion, then 2 trillion galaxies within the observable region alone. Every time we looked, the universe was larger than we thought. And here is the pattern. Every model that humans have built to contain the universe has, without exception, turned out to be too small. The observable horizon at 46.5 billion light-years is the largest thing we can currently constrain. But the pattern of the last 5 centuries of cosmology is consistent. The actual extent of the universe is larger than the model predicts. Every tool we build sees further. Every measurement pushes the boundary out. There is no reason to believe that the boundary we have identified today is the final boundary. There is also, strictly speaking, no way to rule it out. But the history of the question gives it a direction, and the direction points toward more. Further, larger, and tonight, lying in the dark, you are the most recent point in a chain of observers that stretches back to the first human being who tilted their head toward the night sky and wondered what was up there. Every one of them was standing at the center of their observable universe. None of them could reach its edge, neither can you. But you know something none of them knew. The edge is not the end. It is a horizon. And beyond it, the universe continues. For as far as anything goes, you live inside a galaxy that is 100,000 light-years across. Not approximately, not roughly. The Milky Way's disk spans approximately 100,000 light-years, give or take the thin disk where most of the visible stars reside, surrounded by a thicker disk, a bulge at the center roughly 10,000 light-years across, and an extended halo of dark matter that reaches well beyond the visible structure. The solar system is located roughly 26,000 light-years from the galactic center, not at the center, not at the edge, but in a relatively unremarkable position in one of the galaxy's spiral arms. Light takes 100,000 years to cross the Milky Way. The signal we receive from the Voyager spacecraft, humanity's most distant artificial object, takes roughly 22 hours to travel between Voyager and Earth. Voyager has been traveling for over 46 years and is now about 224 astronomical units from the Sun, roughly 22 light-hours away. 22 light-hours is our record for distance reached by a human-made object. The Milky Way is 100,000 light-years across. Our record reach is 22 light-hours. To cross the Milky Way at Voyager's current speed would take roughly 1.7 billion years, and the Milky Way is one of the smaller galaxies in the observable universe. The Andromeda Galaxy is larger. The Triangulum Galaxy is a small satellite. The Virgo cluster, the nearest major galaxy cluster, contains over 1,300 galaxies within a region roughly 8 million light-years across. The observable universe contains 2 trillion galaxies, not 2 trillion stars. 2 trillion galaxies, each containing billions to hundreds of billions of stars. And in an infinite universe, that number of galaxies extends without limit the same density of matter, the same structure of the cosmic web, repeating and continuing in every direction on scales that make the observable universe small. Our most distant spacecraft is 22 light-hours away from Earth. The observable universe is 876,000 light-years across, per light-year of travel distance, 46.5 billion light-years in every direction. The ratio between what we have reached and what we can see is not a gap, it is a chasm. And the chasm between what we can see and what exists in an infinite universe is not a chasm at all. It is the whole. The early universe had a sound, not sound. In the way you'd hear it in a room, there was no air, no atmosphere. no medium that would carry vibrations in the way human ears are designed to detect. But the early universe, in those first 380,000 years before recombination, was a plasma, a hot, dense fluid of protons and electrons, coupled to photons, and in that fluid, pressure waves propagated. They were called Baryon acoustic oscillations. Regions of slight overdensity attracted more matter via gravity, which compressed the plasma. But the compression also increased radiation pressure, which pushed back. The plasma oscillated, compressed, then expanded, then compressed again like sound waves in an extraordinarily hot, high-density medium. Those oscillations propagated outward from every slight overdensity in the early universe. They traveled at roughly half the speed of light, the sound speed in the early plasma. For 380,000 years, the universe rang. When recombination happened, when the fog lifted and the CMB photons scattered free, the oscillations froze. The pattern of those frozen pressure waves was stamped onto the distribution of matter in the universe, and that pattern is still visible today, 380,000 years later, imprinted on the large-scale distribution of galaxies. Astronomers call it the Baryon acoustic oscillation peak, a preferred scale in the clustering of galaxies, a slight excess in the number of galaxy pairs, separated by approximately 500 million light-years. That preferred distance is the distance those early pressure waves traveled before the universe became transparent. It is a fossilized sound wave from the early universe, and it is used today as a standard ruler, a known physical scale that can be compared at different distances in the universe, allowing precise measurements of the expansion history and the effect of dark energy on that expansion. The universe at the beginning rang like a bell. The echo of that ringing is still written across the distribution of every galaxy in the sky, and the reason it was ringing, the slight overdensities that seeded those pressure waves, traces back to inflation, to quantum fluctuations in the first fraction of a second, stretched by inflation to cosmic scales, imprinted on the CMB, frozen into the acoustic oscillations of the early plasma. The sound you're hearing in the background, if you know how to listen, is the echo of the universe's first moment. It has been traveling for 13.8 billion years, and it is still carrying information. Numbers can lie, not by being wrong, by being too abstract to land. 10 to the power of 80 atoms, 46.5 billion light-years, 2 trillion galaxies, 10 to the power of 10 to the power of 29 meters to the nearest copy. These numbers are real. They represent real distances, real quantities, real physical objects. But the human brain did not evolve to feel them. Evolution calibrated our intuition for the African savanna, for distances of meters and kilometers, for timescales of days and years and generations. Cosmological scales are not accessible to intuition. They can only be accessed through mathematics. But there is one comparison that occasionally breaks through. If the entire observable universe, all 46.5 billion light-years, all 2 trillion galaxies, all the CMB and dark matter and dark energy that fills it, were compressed to the size of a single atom, the distance to the edge of the minimum inflationary universe would be approximately 10 to the power of 23 meters. 10 to the power of 23 meters. That's roughly 10 million light-years, larger than the local group of galaxies. From a starting point of one atom, the observable universe is the atom. The minimum extent of the total universe is 10 million light-years from that atom, and that's the minimum. If inflation lasted longer, and most models predict it did, the ratio is correspondingly larger, possibly by factors that have no upper bound. The observable universe is not a sample of the whole. It is smaller than a sample. It is closer to a rounding error, and you, the specific configuration of atoms that constitutes you, lying in the dark tonight, are embedded in a universe where the scale of what exists makes everything observable look like an afterthought. That's not meant to diminish you. The observable universe is still 46.5 billion light-years across, and still contains 2 trillion galaxies, and still produced you. And you, in your specific position, at the center of your specific observable sphere, are the only observer who has access to exactly this slice of the cosmos. But the full scale of what exists, if infinite, makes the word vast seem like an understatement so extreme it becomes meaningless. The universe is not vast. Vast is a human word, built for human scales. The universe is simply what it is, and what it is goes further than any word we have. Here is the cleanest statement of what the infinite universe implies about you. Not eventually, now, somewhere in the infinite volume of space. Right now, every configuration of matter that does not violate a law of physics is instantiated. That includes configurations almost identical to this one, and configurations identical to this one. The specific arrangement of atoms that constitutes you, your brain, your body, your exact neural state at this moment, is one configuration among a finite number of possible configurations within a given volume. Finite because the number of atoms is finite, and the number of possible arrangements of any finite set of atoms is also finite. Finite arrangements, infinite space. Every arrangement occurs. BHPS, particularly every arrangement, the nearest location with a configuration indistinguishable from you, and this moment is estimated at roughly 10 to the power of 10 to the power of 29 meters away. A distance so incomprehensibly large, it makes the observable universe look like a rounding error. But it is a finite distance in an infinite universe. This is not mysticism. It is arithmetic applied to cosmology. And it is one of the reasons that the question, is the universe finite or infinite? The answer changes the nature of identity, of uniqueness, of what it means for anything to be singular. In a finite universe, you are unrepeatable. The specific configuration of atoms that constitutes you exists once, here, now, and nowhere else. In an infinite universe, you exist infinitely many times. Simultaneously, in regions so far away that no information can ever travel between them. The mathematics does not know which version of you is the real one. There is no center. There is no original. There is no special coordinate. There are just configurations, infinitely many, in an infinitely large space, running in parallel, forever. And there is no experiment that could ever distinguish between the two scenarios. When you sleep tonight, the universe will continue. The Milky Way will continue its orbit around the galactic center, moving approximately 230 kilometers per second through the galaxy, covering roughly 20 million kilometers before you wake up. The Andromeda Galaxy will have moved approximately 9.5 million kilometers closer to us than it was when you closed your eyes. It has been doing this for billions of years. Somewhere in the observable universe, a star will be born in a collapsing cloud of gas and dust. The same process that formed the Sun 4.5 billion years ago, now happening somewhere in a galaxy you will never see, around a star that will never have a name. Somewhere, a star will die. An outer layer will expand, cooling and glowing, drifting into the surrounding space. A white dwarf will remain, smaller than Earth, dense as a million Earths, radiating the last of its stored heat into the dark. Somewhere, two neutron stars are spiraling toward each other, the same configuration that produced a gravitational wave signal detected by LIGO in 2017. They will merge. The collision will produce a kilonova, an explosion 10,000 times brighter than an ordinary nova, synthesizing gold and platinum and uranium, elements heavier than iron that can only form in that specific violent context. The gold in any piece of jewelry you own was formed in a collision like that billions of years ago. And somewhere, further than any photon will ever carry information to you, in regions of the universe permanently beyond the cosmological horizon, the same processes are happening: births and deaths of stars, formation of planets, perhaps the evolution of life, perhaps the emergence of observers wondering about the extent of space without any knowledge of your existence and without any possibility of ever acquiring it. The universe does not pause for sleep. It has not paused once in 13.8 billion years. When you wake, it will have continued. It will have continued without record, without witness, without transmission of that continuation to you. You will simply find yourself at a slightly later moment in a universe that has moved on without asking, and the horizon will be in the same place it always is. 46.5 billion light years in every direction. The same boundary. A slightly older universe. Still expanding. Still without end. Let's be specific about what we know, not what we suspect, not what the models suggest, what we actually know. Measured, confirmed, and published in peer-reviewed literature with error bars and independent verification. We know the universe is approximately 13.8 billion years old, measured from the CMB power spectrum, from the ages of the oldest stars, from the expansion rate calibrated by multiple independent methods. We know the observable universe has a radius of approximately 46.5 billion light-years computed from the age, the expansion history, and the curvature measurements. We know the universe contains at least 2 trillion galaxies within the observable region measured by combining galaxy count data from Hubble with gravitational lensing surveys. We know the universe is flat to within 0.2% measured by the angular scale of acoustic oscillations in the CMB by the Planck satellite. We know the expansion of the universe is accelerating measured by the light curves of type Ia supernovae across a range of redshifts, independently confirmed by the CMB, by Baryon acoustic oscillations, and by the growth rate of large-scale structure. We know dark matter exists inferred from galaxy rotation curves, gravitational lensing, the CMB power spectrum, and the large-scale structure of the universe. We know dark energy constitutes approximately 68% of the total energy content of the universe constrained by multiple independent datasets. We know the CMB is uniform to 1 part in 100,000, measured by Planck, WMAP, and earlier missions. We know the large-scale structure of the universe, the cosmic web of filaments, voids, and clusters, matches the predictions of a model that assumes cold, dark matter, dark energy, and initial conditions consistent with inflation. All of this is known. What we do not know, what is genuinely, currently, honestly unknown, is whether the universe extends infinitely beyond the observable region, or whether it is very large but finite. And if finite, what its total size and topology might be. That question cannot currently be answered. It may never be answerable, given the limits imposed by the cosmological horizon. But here is what the totality of that knowledge implies. The universe we can see is geometrically flat. That flatness, in every model that fits all the other data, is consistent with infinite extent. The physical processes, inflation, dark energy, the dynamics of an expanding universe do not stop at the observable boundary. They continue. There is no mechanism in current physics that would cause space to end at or near the observable horizon. The universe does not end at the horizon. It continues. How far? As far as the physics goes, and the physics, as currently understood, goes without limit. That is the answer the universe is able to give tonight, and it gives it in the same language it has always given its answers. In the light that travels across the void, in the temperature fluctuations imprinted on an ancient background, in the geometry of space, measured by a satellite orbiting the Sunday, the universe answers the question, it can. You are here to receive the answer. And that, in itself, is not nothing. Something unusual about gravity. It reaches. Every other force in physics, electromagnetism, the strong nuclear force. The weak nuclear force has either a finite range or is blocked by intervening matter. Electromagnetism technically has infinite range, but it is also easily shielded. The nuclear forces operate only at nuclear scales. Gravity reaches everywhere. It is not blocked. It is not shielded. It weakens with distance, following the inverse square law, but it never reaches zero. and this has a specific consequence for the cosmological horizon. The observable universe is defined by light, by the finite speed at which electromagnetic radiation propagates. But gravity is not limited by the cosmological horizon in the same way. The gravitational influence of matter beyond the observable horizon is already present in our universe. The Great Attractor pulls at us from a direction where, behind the plane of the Milky Way, we could barely see for most of history. The Shapley supercluster, roughly 700 million light-years away, exerts a measurable gravitational influence on the motion of our local group. These are within the observable universe, just barely mapped in some cases. But the principle extends. Matter beyond the observable horizon exerts gravitational influence that has been propagating toward us since before the horizon was the horizon. In the very early universe, regions that are now beyond the observable boundary were close enough to be in causal contact. Gravity from those regions reached us during that early period. The influence is already here, already affecting the distribution of matter in the observable universe. The flatness of space, the zero curvature that Planck measured, is partly a consequence of the gravitational influence of the full extent of the universe, not just the observable portion. An infinite, homogeneous universe has a specific gravitational signature that contributes to the flatness we observe. In this sense, the universe beyond the horizon is not completely invisible to us. It left gravitational fingerprints in the early universe that are encoded in the CMB, in the large-scale structure, in the flatness we measure today. The horizon hides the visual record of what lies beyond it. It does not hide the gravitational record. Gravity reached past the horizon before the horizon existed. And what gravity encoded in the early universe, we can still read. Not everything. Not the current positions of galaxies beyond the horizon. Not whether there are observers there looking back at us. Not the specific configuration of matter in those regions today, but the statistical properties, the scale of density fluctuations, the overall geometry, the expansion history. These bear the imprint of the full universe, infinite or finite, not just the observable slice. The universe beyond the horizon is not completely silent. It speaks in the only language that travels faster than light, the language of geometry, of curvature, of the shape of space itself. And when we measure that shape, when the Planck satellite found zero curvature to within 4 decimal places, we were hearing, in some sense, from the full extent of the universe. Not seeing it, hearing it, in the language that predates light, in the geometry of space that was set at the moment of inflation, before the first photon ever propagated, before the first atom formed, before any observable boundary existed. The full universe spoke first, in gravity. The observable universe answered in light. And you are here, at the intersection of both records, in the dark. You came tonight looking for the edge. You won't find it. Not because it doesn't exist, but because the universe is not structured to make it findable from inside. Every measurement you can make, every photon you can receive, every gravitational wave you can detect, all of it comes from within the observable sphere. All of it tells you about the universe as it was, as it is within your horizon, as it has been since the Big Bang. What lies beyond is real. It is there. It obeys the same physics. It is made of the same matter and dark energy. It is expanding in the same way. It is structured by the same web of filaments and voids. It just cannot send you a message. Not because the distance is too great, because the expansion of space between here and there, the accelerating, relentless, dark, energy-driven expansion makes the gap uncrossable by any form of information. The universe is not hiding the edge from you. The universe doesn't have a concept of hiding. It simply is what it is. Flat, expanding, filled, extending. And the part of it you live in, the 46.5 billion light-year sphere centered on you, is already more than you can see in a lifetime, more than can be fully mapped in the history of any civilization, more than could be physically visited at any speed for any duration. The observable universe is enough. It is, by every measure, more than enough. And beyond it, in the dark, the universe continues, without edge, without end, without waiting for you to catch up.